RLC, like with K and everything. Okay.
Yeah. So we will.
I was. Yeah, you guys have been 36. I say the whole class teams up.
One way to get it done.
Really careful.
I don't mind. I don't mind you guys helping each other. Just write it up in your own words. So. Well, you can like be like, okay, here's my circuit. You build the same circuit, and then I tested mine. What did you get? You test yours. Okay.
Both people are due.
Both people just do it, and I don't mind you working together. So. This is weird or not. Sorry, say that again. So which you can write as minus J over C omega.
Yeah, okay.
Oh, can't see that one there. Okay. I need to move that. There we go. Okay. All right, well, welcome. Welcome back after holiday weekend. Hope everybody had a fun time. I'm going to be trying the lecture a little different, as you can see. So hopefully these will work better for the recordings. I don't know if it's going to be weird, though, to see like me there and there. So we'll see kind of how it goes. Please give me feedback if it is like, this is weird. Or if you feel like it's better, any type of feedback is great. So we're moving, last week we did RL and RC. So we're now moving into RLC. And so anybody want to take a stab at summary for RC and RL? A summary, yeah. Yeah.
So RL is they're both gonna be final minus the parentheses of initial minus final. And then for RL, it'll be e to the negative t times L, or yeah, t times L over RTH, or is it RTH times t over L? It's negative t over tau.
Just a sec, let me write this one. Final. E to the minus t over tau. So then tau you're saying for capacitor is what? Let's do that one.
For capacitor, it's
Yeah.
RTH times C.
Uh-huh.
And for an inductor, it's L divided by RTH. Is it RTH divided by L?
No, it's inductance divided by L.
Okay, yeah. So then, yeah, it's negative T times RTH.
Okay. All right, what other summary? Other
Oh,
things you remember? Yeah.
yeah, when the capacitor is charging, it's open circuit.
So it's sitting, after it's been sitting,
Okay.
it will be, capacitor will be open. And inductor will be short, correct. If I can spell, short. All right, other comments about RC? How many times do you need to redraw the circuit? Okay. 3. So 3 redraws. 1 for initial. 1 for final and 1 for tau. What position does tau need to be in?
Fine.
Correct, fine. Okay, any other comments? You guys feeling comfortable with the RC and RL?
Yeah.
Okay, comfortable enough at this stage, so.
Yeah.
Homework this Friday or Thursday is homework will be due. It will be RC and RL circuits to solve them. And then your quiz on Friday will be RC and RL. Okay, so it will randomly choose on the quizzes. It will pull from a database. So some of you may get RC circuits, some of you may get RL circuits. So they should be unique to everybody because I have like 150 problems in there. So Thursday assignment, which is the discussion. So make sure you post your discussion question. If you don't have a discussion question, you can even like post like, this is my rewritten wording for something, something that's going to kind of help you. So that's the goal of the discussion is like, put it out there and then look and see if you can answer somebody else's question. So that helps you to think about how can I explain this to somebody else? That is a way to learn the material too. Okay, so that's the goal of the discussion. So if you don't have a question, feel free to like, okay, well, this would help me to summarize these in my own words and then post that. Okay. Other comments. Lab should be going on this week. So make sure you go to lab and start the new lab experiment. You're gonna have 4 labs. You're gonna only have to write up 2 of them. The first lab will be more of a formal report and the third lab will be a formal report. And then the second and fourth is just the notebook itself. Well, all 4 of them will be notebooks, but the first and the third, you'll need to write up more of an official final report just to get practice doing that. And so you do that instead of a final project in this course. So that's the trade-off with this course. Just a little bit different than some of the others. So you don't have a final project, but you do have a little bit more writing that you'll do instead. But once you get done with the 4th lab, you're done. So you can usually get done a little bit earlier in this class so that if you have other final projects, you can focus on those. So that's kind of nice. So do stay up on the work in the labs so that you don't get behind. If you're struggling with the material in the lab, feel free to go to any other lab sections those weeks and get extra help with the TAs, okay? Or you can also set up one-on-one times with the TAs for the lab, or the grader who you met, Brittany, is also one of the lab TAs, and she's very open to meeting with students, and she's already set up her office hours. So you can attend those and get questions about use her as a tutor for this class, okay? She will be awesome. Any questions, comments about the material we've done so far? Yes. Correct. Yes. So do make sure you're keeping snippets if you're using online calculators, online programs. If you're creating your own program, make sure you're taking snippets of that and including it in your work that you submit, so that if you have errors in your coding, then that can also be commented on. And then, yes, again, if you're using an online tool, make sure you take a snippet of it in case you typed it in wrong, then you can get the credit for that too. And yes, you'll get partial credit. So it will come back automatically if it's fully right. And if it's wrong in any way and you're not close to the answer, then you'll get partial credit that will be graded after the fact. So don't be discouraged if you do it and you get a 0 and you're like, wait. But do make sure you do write down all your work that you want to get partially graded, and there'll be a submission button of a file. So you'll need to combine that. And so have that ready before you start the quiz. Yes. Yes, quizzes are only one attempt too. And so they will open up Thursday night at, I think, 5 or 6, and then they will close by midnight Friday night. So if you even want to get them done on Thursday night, you can get them done on Thursday night before class even. Okay. All right, any other questions, comments? Yes. Everything is open notes, open book, open computer. So, as mentioned before, I think, I don't remember if you were the one asking, you can use online calculators. You can use scripts if you want. Yes, there will be, well, I think I worded those that it doesn't matter if you can do them in MATLAB or not. So yes, I will be specific if you cannot use that MATLAB. But yes, you can use MATLABs. You can use MATLAB scripts if you want, if you're comfortable with that. And I encourage you to do those. Some of the students do that beforehand, knowing what kind of is coming up. And then they'll put in like, what is my R value? What is my C value? And then it will kind of pop it out for them. So if you want to do that, you're fine to do that.
Is this something that you'd encourage, or is it only like a couple in every class?
I usually only have a handful in every class, but you're welcome to. I mean, you are welcome to, if you feel more comfortable coding, go for it. I do not discourage that.
Is it on job descriptions?
It's easier, I'll say that, and you don't make as many errors. So real life, you're going to use it. So I'm not going to discourage that. Yeah, so you can take your exams on your laptop if you want, instead of the computers in the lab. But everybody else will be meeting in the lab upstairs in the Engman lab, and we'll be taking the exams online. So it will either be the computer there or your own computer. Just make it sure it's charged. I had a student that came in and it was totally dead. So do make sure your computer's charged. Tablets, if you're using tablets, are charged. Whatever you're going to use, just make sure that they're accessible. As you're doing the quizzes, you'll get comfortable with what method you like to upload. So make sure you bring whatever that is, if it's your phone, if it's a tablet. They do have a scanner upstairs, but it's a little clunky. So if you can just use your phone, is most of what the students use in here is their phones. So just make sure you have the apps on it and that it's working well.
The only thing I saw limits for this an exam would just be like LP spice signal
Right.
and whatnot.
Yep. So that's the only thing, that and peers and Chegg and any other online tutors are off limits. Yes. Okay. Any other questions? Okay, you guys ready to move to? Oh. Sorry. Okay, so we're going to move into the derivation of RLC now. So what do we know? So whenever I approach a problem, I like to say, what do I know from this problem? So looking at this, what equations do you already know? So if I'm trying to solve this for, I solve it for, for series VC. So say I'm trying to solve this for VC of T. So what do I know in this problem? Yes.
we know, the equations for the capacitor and the inductor, we also know, Kirchhoff's laws.
Okay.
That we can use to help combine those into an expression we can solve.
Great. So we know VL is what? The equation for VL. Go for it.
L times, the derivative of the current inductor.
Correct. And VC, or sorry, IC. What's the equation for IC? Okay, so we know those. So now we have an equation, right? We have VC here. But that's not really helpful, right? So in that we look at, okay, C we're assuming is known. So no RLC. So say we know those and we know the voltage VS. So these are all our known values. So from here, we want to write that loop. So I'm going to label IC through each of these, and it's going already in this direction. And so it's not going to help me, right, to know what the initial value here is, right? Because what's going on? Correct, zeros. Okay, so we would do the same thing we did before, which is draw the circuit with it in the switch in the first position. So in this case, it would be open. And then IC is going to be 0, VC will be 0. So we really want to look at it now in the final position or after that switch is closed. So now if we take a loop, we are going to have, if I start here and go through in this direction and I circle all my second signs. So I have plus VS minus, correct? And then what there? You can't do IC times L, right? So you're going to have to write the equation for VL. Right, we know what VL is. And then again, same thing with VC. We don't know. We can't say like I times C, so we just say VC. So for the elements that are time dependent, we just put in VL or VC when we do those loops. And then from here, we can now substitute in for IC and VL equations, we have those. So now we can rewrite this as VS, which is a known value, minus RC dVC dt minus L DIL dt, and IL and IC are the same. Note that. And then minus VC. So what kind of an equation is this? Correct. Second order. Well, I'm not quite to second order. Let me do one more thing first. So note that if I take the derivative of DIC dt, then that's going to differentiate, well, write it this way. And then if I differentiate the other side, this becomes, C is a constant, so that will come out. And then this becomes D squared VC dt. And so now we have the variables all in terms of VC. So what I did here was look at, okay, I have an equation, VC and IC are two unknowns. Is there a way to try to get to just one unknown? And I have IC in terms of VC, so that's why I then looked at, well, if I differentiate it, then I could have that and plug that in now for that LDIC dt.
Are the D's partial derivatives?
No, they're just in respect to time because VC is only, we're only doing a dependence on time right now. So they're partial if they have two variables in the equation. And in this case, we're only looking at one variable for now. But you can actually do other terms in there when you think about like terms of like temperature, which some of these elements will be dependent on temperature too. Then they're becoming partial with that. But in this one, we're just looking at time. All right, so now we have our equation rewritten with just VC. And that DIC dt becomes the sorry, I'm missing a C in there. LC D, there we go. D squared VC. Make that smaller. There we go. Okay. And then that's equal to, or minus VC equals 0. So I just use this term for DIC dt. So now it's a second order in terms of VC. And then from here, we're going to do the same thing where we, not the same thing, sorry. So now we're going to reorder it, yes.
Is that RC, is the C a subscript? Or is that-
Sorry, no, it's R times C. You erase that. Because yeah, that is RC times C. Minus R.
LC?
Yes, L times C. All right, so I'm just going to rearrange here, rearrange this and put the second, the squared term. And I'm going to multiply through for minus. I'm going to turn those all to pluses and then the plus to minus. So this will be a positive LC times the second derivative of VC over dt, and then a plus R times C. And then the first derivative of VC. And then a plus VC. And then I'm going to take the VS over to the other side, so it becomes a minus, and then it becomes a plus on the other side. And then I'm going to divide this all by LC. That will cancel out those C's. And the reason I'm doing this is because now this gets to be a generic form of the second derivative of VC of t plus some A1 first derivative of VT plus some constant times V and equal to a forcing function, which we'll just call C1. So this form, we already know solutions for. So that makes it much nicer that we don't have to go through and actually resolve this every single time. So this can be treated like a x squared plus bx plus c equals 0 would be, I use the term homogeneous solution. So I don't know if you guys heard that one. Okay. Homogeneous solution. So this is when that equation equals 0. And so we can get a solution with that, and then we can get a solution with a forced function. And then you can add the two together. So looking at just this, if you remember, a quadratic is solved by a minus b plus or minus the square root of b squared minus 4ac over 2a. So these will give you the roots of the system. And so let me add another page. We're going to have this form for every solution now. That's a second order. So if we have an R and an RLC or an RLC in series, or we could have an RLC in parallel. So those are the two options that we have for these. So in a series RLC, we call those X roots S1 and S2. And we're going to introduce these two terms, alpha and omega naught. And if you remember, these are called also, this is called a characteristic equation. Anyone remember what those can be? Like if you have b squared minus 4ac, if that term can be greater than 0, right? It can be less than 0 or it can be equal to 0. So those are the three options that you have. And those characteristics are going to show you what form this equation will take. And so those will be your three options, okay? So we're going to introduce now terms alpha and omega naught, where we can just look at the circuit, identify what alpha and omega naught are, and then based on those values, they're going to give us the characteristics of this. So yes.
How are you drawing omega? I'm sorry. Oh, it's just a W, never mind.
So omega is a W with a 0 on it. 0 as a subscript. And then alpha in the case of series RLC is just going to be RTH over 2L. And omega naught squared is going to be what's called the resonant frequency, or you can say it's the square root of 1 over LC. Parallel is going to be the same roots, S1 and S2, except for alpha in this case will be 1 over 2 RTHC. And omega naught will be the same. So what is happening with these circuits? So we said when this is open first, you have 0, right? So we're all going to start out at 0 here. What happens after it's been sitting for a really long time? What happens to the inductor? Short. And what happens to the capacitor? It opens, correct? So now VC is going to be what value after it's been sitting there for a really long time? It will be 24 volts, correct? Because the wire will have no current in it. So there's no current now going through the inductor because it's an open there. And so it will just charge up to that battery. So in the end, we know it's going to be at 24 volts. So we can find an initial value and an end value just looking at any circuit now with L and R's, many inductors and capacitances in there. So we usually can find an end value and a beginning value just by doing a short for the inductor and an open for the capacitor. What we don't know is what happens in between that time. And those are going to depend on the values of L and C and R. Yes.
Go back to the output parallel.
Sorry. Okay. Any other questions so far? Okay. So we have options of how these are going to respond, and they're going to respond differently based on those RTH, L, and C. So because of those three terms, we can have what's called underdamped. And the form that it will take in between that 0 and 24 volts, it looks like a sinusoidal. And that's called underdamped. That's when alpha will be less than omega naught. Then we also have critically damped. That's exactly when alpha equals omega naught. So when it's critically damped, this is really, looks like it's just charging up, right? So this kind of looks like what we had before with just the RC. Then we have overdamped, which is going to be when alpha is greater than omega naught. And so that undershoots the 24 volts, and it takes it even, looks like a little bit longer to reach 24 volts. So you can see here the time constants are going to be different for each of these two.
Will still eventually reach.
Yeah.
this, right?
Correct. Yep. But it takes it longer, or overdamped takes it longer. Critically damped is the most efficient to get to the end value. And then underdamped will get there quicker, but then it will oscillate right around it. Yes. So I'll show you the equations in a minute.
How is it possible to have more like energy stored in your capacitor than you have volts being put into the circuit?
So that's a different question and a very good realistic question. So what happens is it will never reach 24. So what it does is actually settles lower than 24 volts. So it will be less than 24 volts
Okay,
because of the
so-
realistic values that
Okay,
go
so
on.
just-
This is theoretical, yes. So yes, in lab, if you built this, you actually would never see an N 24 volts. It's always going to be a little bit less than 24 volts. Uh-huh. Yeah, so the peak of it would actually hit 24 volts because you can't have more energy in there than you can actually supply. So it would actually hit a peak of 24, oscillate, and then go close to like 20, 22-ish probably would be about, you'd lose probably a couple volts in there. So, because of the actual, like, so again, like we use ideal components that never lose energy. And realistically, no, they do dissipate in there due to many different reasons, but.
Are they critically damped also? But if you like that.
I mean, it will be closer like 23. I mean, all of them will kind of be like 23 point something. But so eventually they'll all be that same value, no matter which ones you use. It's just how quickly will they get there. So underdamped will spike up and it will actually get there like at different periods because it's going to oscillate. It will reach that value you want. So it depends on what you want to do with the circuit. So if you're just trying to like, oh, I want a trigger, you would probably underdamp your system so that you can peak it really quick. But then you don't want that oscillation to affect any other circuitry in there. So you would want to say like, well, will that create other issues in there or not? Critically damped is going to be a little bit slower, but it will be easily, there's no noise that will be introduced in there. So we consider that oscillation kind of some noise that you introduce into the circuit with an underdamped system. And so it depends on kind of your applications too. Overdamped will be where you're like, okay, I want to make sure I'm slowly getting up there so it doesn't affect any other things in my circuit. So all of it is going to be application based of what do you want to achieve in the end. Okay. Yeah. So you want to just be aware of each one and what they're good and bad for, kind of a thing. Does that make sense? Okay. All right. Sorry. Not. I don't know how to, okay. I'll figure out how to not turn this off next time. Okay. And then if it's discharging instead, so we looked at just the one that was just charging. When it's discharging, we can do the same thing. When it's in position 1, it will start off right at VS value of 24 volts. And then when it opens or goes to the short circuit, then it will discharge till it's almost to 0. So similarly, you'll have underdamped, critically damped, and overdamped. Okay, so these coefficients of alpha and omega naught, alpha is called the damping coefficient. And that is actually going to be measured in a new unit called Nepers per second. NP over S. You're going to love this semester because you're going to learn a lot of new units. So Nepers per second. Don't know where that came from. If anybody wants to look it up and share next time where Nepers came from. Omega naught is the angular frequency. It will be still in radians per second. So omega naught or omega usually is always in radians per second, and it will always be your angular frequency. Angular frequency is related to hertz, which we're more familiar with. When we look at a sinusoid, we usually do it in hertz, and then that conversion is omega is equal to 2 pi f in frequency. So you can change from angular frequency into hertz, which you're more comfortable with probably. But note that all of our equations will always be in omega. And when you measure things, you'll have to convert them to get to the mathematical form from hertz into omega. Okay, so take that note too. All right, so now when we're solving these kind of circuits, we know that we have some general forms. So I'm not going to go through all the derivation because we don't need to, right? We already know where it comes from. And we're just going to say like, okay, if it's of this form, then we're just going to use these equations. We will need to find every value within there with those 3 redrawn circuits. So an initial circuit, a final circuit, and then we're going to use final values. For VC infinity would be the final value. VC of 0 would be the initial value. And IC of 0 be the initial value. So we have to note though, when we're looking at VC, we have to take that extra step to find IC. So we have to redraw the circuit with a, for a capacitor, it will go to a voltage source. And for an inductor, that will go to a current source. And we use those to then find the other initial value. Yes.
So these equations are showing the solved DQ with the combined modulus and force solution.
Correct. Yes. So we do not need to do them separately either. So it's all combined, which makes it really nice. So what we're going to first do is identify, did I write these down? No. Okay. So the first step in these is going to be to identify, do we have a series or parallel? Because that is going to determine which equation set we're going to use. So we are going to use the final circuit to determine what configuration do we have, whether it's series or parallel. From there, we're going to calculate alpha and omega naught. And what do you think we need to do to then, because what do we need to know? First, we needed to know, is it series or parallel? Now, what do we need to know to solve this? Correct. We need to know the damping stage. So is it overdamped, critically damped, or underdamped? So we're going to compare alpha to omega naught, and that will help us to determine which of these boxes we're going to use. Okay. So compare and determine overdamped, underdamped, or critically damped. Oops. Then from there, we need to find variables, unknown variables for the equation set. And then you can just plug in the equations. So it sounds really easy, right? So once we've narrowed it down to an equation set, you can see here like overdamped is going to be of exponential forms. So it's A, which is going to be determined from initial and final values and the characteristic roots, S1 and S2. And those S1 and S2 are going to be the exponential forms. So that makes sense because overdamped, well, it doesn't totally make sense. Never mind. And then the final value. Critically damped, we are going to see, again, still the exponential form, but now we have T in it. So we have B1 times T in there, so it gives that different form of that exponential. And then the underdamped is going to be a combination of cosines and sines. And so that's where you get the oscillations. So that one makes more sense, I guess. All right, questions? Yes.
Does it matter what would be the
No. So it will not matter as long as you can determine what form it is. So let's go through an example. So with this, we're going to look at it in the final state. So where's the switch in the final state? Correct. Open switch. And so what does it look like for the C in comparison to where the L is? Do those look like they're in series to each other or in parallel to each other? Series, correct. So this would be a series RLC. So you're going to look at the relationship with the R, not the R, the L and the C are going to be the critical positions of whether they're in series or parallel. So we would say this is in series, and then what's our next step? We need to know what to solve before that. Correct. Alpha and omega naught will be needed first before we can go to what variables do we need. So alpha for series is RTH over 2L, and omega naught is square root of 1 over LC. So to determine this RTH, again, you're going to use the final state. So with these in series makes it easier because you can put the A and the B. You can move these so that they're right next to each other. And then there's your A and B, and you leave the, let me redraw it. Right, look, I have a confused look on people's places. So copy. All right, so remove all this. Okay, so then to find RTH, it's just you put the A and B where the elements are and take out the R and the C, and all you have left here is 20. So that makes it easy where RTH is. All right, so alpha here will be 20 over 2, and L is given as a 10 micro. Micro is what? Correct. And then square root of 10 to the minus 6. And nano. Correct. So this gives a 1 times 10 to the 6 for alpha in what units? What's the unit for alpha? Yes. Meters per second.
I looked it up, by the way, they're named after John Napier, who invented logarithms.
Okay. Thank you. No idea why that ended up being in here. So meters per second. So he was the one that invented logarithms.
That's invented this, but there's not the philosophical discussion there. Wikipedia uses the word invented.
Invented logarithms.
Google search, I would not cite that.
All right. Well, named after him, the individual who, how would you say that correctly?
Discovered, you stumbled across. I don't think so.
Derived would derive, no, derived wouldn't be it either. So whatever word you want to say. Yes, that's a great one. I like that one. Who we attribute logarithms to. So meters per second, and then omega naught is also 1 times 10 to the 6. And what's its units? Radians per second. There you go. So radians per second. So what is this one going to be? So we go back up to the table. We're series. On this side is series. And this side is our parallel. So series, and we are, what did I say? Critically damped here. Or we're equal, so we're critically damped. So we're going to use this set of equations. And now we need to find B1, B2, alpha we know, VC0, VC infinity, and then IC of 0. So those are going to be the elements or the variables in here that we need to find. So we do an initial drawing, and in the initial, we're going to redraw just like we did before, leave out the 3 elements. So the switch, the inductor, the capacitor. And then we're going to redraw what those look like. So the switch in the beginning is closed, and then it opens up. Thank you. So it's closed, and then the inductor sat there. So what's it going to be? Not quite yet. Before that. Correct. A short, and then the inductor or the capacitor is an open. All right. So now we're going to find, oh wait, I drew these backwards, sorry. VC is up here. And then you want to make sure on these that you're labeling the VC the same polarity as it was originally. Okay. So that can be a little bit of a trick if it's not polarized. So you need to just make sure that the plus and minus of that stays the same direction. So you find the values in the correct way. All right. So VC here, how do I find that one? Do what? So, as you know, I love node voltage. So I am going to place a ground on the bottom. And then this is going to be what if that ground is there? That node will be VC. Yeah, so then I would go into what you're doing the node voltage equation. So VC minus 24/10, correct? And then solve for VC. And I get 16 volts. Actually, I'll write these out first. So I combine my like terms, take over the 24/10, and then this becomes 2/20. And so 24/10, and then this is 20/3. And so, let's see, 2. And then this goes in 8, right? 8 times 3. There we go. So 16 volts. So this will be my initial value for VC. And IC, we need IC of 0. So IC of 0 where did I? IC. I'm going to take back what I said. So IC of 0 can be found from this, and it's just going to be 0 in this case. All right, so final one. Leave out the switch, leave out the inductor and capacitor. Now determine what the switch position is. So where's it going to be now? Correct, open. And what do we do with the capacitor? Is that correct? Correct, open. And the inductor? The inductor becomes a short. So now what do we have for VC? Yeah. So yeah, VC over 0, which will be 0. Or VC over 20, which will be equal to 0. So VC is 0.
So anytime the final state doesn't have any like sources in it.
Correct. And the same with the initial, like sometimes you may not have anything connected and then it becomes connected. So it would be 0 in those cases. So now we have all the values we need. We have VC 0, which is 16. VC infinity is 0. IC is 0. VC of 0 is 16, or sorry, yeah, 16. And VC infinity is 0. So now we can plug all of these in. And we have this one up here, get values for B1, B2, and then plug it in for that. So B1 is, copy. Correct. 16 minus 0, so 16. And B2 is 0 for IC, and then alpha was 10 to the 6, or 1 times 10 to the 6 for alpha, and then VC 0, 16, and so this is just 16 times 10 to the 6. And then VC of T is going to be 16 plus 16 times 10 to the 6 T, E to the minus alpha, which is 1 times 10 to the 6 T, And then plus 0, VC of infinity was 0. So this will be volts. And what do I put on the end of this? U of t. So this is only valid once I'm after t equals 0. Or you could write it as just for t greater than or equal to 0. So this would be my end answer. All right, questions? Yes.
So. This. Never mind, I'm gonna get cells.
Okay. Yes.
That's volts, U of-
This is the, here, I'll write, let me write, U of t, and this is in the units of volts. Because this is only valid after t equals 0. So remember, U of t is like a way of saying, instead of saying for t greater than 0, you just write U of t instead. So that's why. Okay, so Wednesday we'll do more problems. So go through the online learning materials for RLC and second order. Get very comfortable where these equations came from. You don't need to know how to step-by-step derive them, but we're going to look at applying them. But you do want to understand kind of where they come from, because that helps you to know like, oh, well, I want to find the end circuit for that value. Okay. All right. Any other questions? Yes.
As far as the, series versus we're just looking at the relationship between the C and the vector not, it's like. what's the other relationship?
Great. So looking at like this circuit, when T is over to the left, you can see that, oh no, that's not a good one. Oh, I don't have one in here. Okay, I don't have a parallel one. But you'll see that they'll be in parallel and R will be usually in parallel to those. So, yes.
What if you had like multiple of like someone else and that's
So you'll want to combine as much as you can. And then we're going to learn the technique after this will be on how do we solve those circuits when they're not in an RLC series or parallel form. So we're gonna go into Laplace, and then we'll look at Fourier to solve those type of series or circuits too.
So in our last circuits, when we class, why don't we like learn how to solve RLC equations using phasors? That way.
Phasors is another way of solving these.
Okay.
And so Laplace is a little bit more, gives you more information about it. With phasors, you were only able to solve it for one specific input
Okay.
when a frequency was at one input frequencies. Now we're going to look at over a whole bunch of different frequencies. Can we solve this for a generic form?
So this is the start
Uh-huh.
of, okay.
Yep.
Thank you.
All right. Have a great day. Yes, this recording is available, Daniel. Usually the day after, it will be in the modules under, sorry, handouts and lectures. So it's in the module section under handouts and lectures. And you can go back and watch the other videos of past lectures that you may have missed. Have a great day.